A pink swatch sits on a screen. 3 numbers describe it: 255, 192, 203. Red, green, blue. Now a question. Should the text on this swatch be light or should it be dark? A small program answers. Light. Confidence? 89%. The program never read a contrast formula. It was never told what readability is. It was never shown the W3C accessibility tables, the rule about luminance ratios, or anything a graphic designer would consider a first principle. It looked at 3 numbers, fed them into what its own author calls a mystery math box, and out came a probability. So what exactly is inside that box? How does a small piece of arithmetic take 3 integers and answer a question about how a human eye reads contrast against a background? And how did it come to agree with a designer it never met? The box is a neural network. Stripped of its mystique, a neural network is a multi-layered regression. Inputs flow in, weights multiply them, biases shift them, nonlinear functions filter the result, and somewhere on the other side, an answer falls out. That is the entire pattern, repeated. The task here is classification, not predicting a continuous number like a house price or tomorrow's temperature, but choosing between 2 categories: light font, encoded as the number 1, dark font, encoded as the number 0. The output the network actually produces is not exactly 1 or 0. It is a probability between them, a number like 0.89. The decision rule on top is a threshold. Above 0.5, we call it light. Below, we call it dark. Everything else is degrees of confidence. The inputs are equally plain. 3 variables: R, G, and B. Each one a number from 0 to 255. Pink lives at 255, 192, 203. White is 255, 255, 255. Pure red is 255, 0, 0. Black is 3 zeros. Every color you can render on a screen is a single coordinate inside this 3-dimensional cube, 16 million points wide. So the contract this network signs is simple: 3 numbers in, somewhere between 0 and 255. 1 probability out, somewhere between 0 and 1. Nothing about luminance. Nothing about gamma curves. Nothing about how the human retina actually behaves. The whole question of this video is what happens in between, in the box, that lets this minimal contract approximate human judgment. Inside the box are layers. The first is the input layer, which is nothing more than the 3 RGB values being made available to whatever comes next. The last is the output layer, a single node that produces the probability. Between them sits 1 hidden layer. In the textbook example we are following, the hidden layer has 3 nodes. Each hidden node is connected to every input. 3 inputs. Times 3 nodes gives 9 weights, labeled W1 through W9, plus a bias for each hidden node. 3 biases. Then the hidden layer connects forward to the single output node. That adds 3 more weights and 1 final bias. Roughly 19 tunable numbers in total, small enough to fit on the back of an envelope, large enough to be useful. What does a single node actually compute? A node is a linear function in disguise. Take the inputs, multiply each one by its weight, and add the bias. The result is a weighted sum, a single number. If we stop there, the whole network would be a stack of linear regressions. And stacking linear functions just produces another linear function. The whole 19-parameter structure would collapse into one straight plane through 3-dimensional color space. What rescues the network is the activation function. After each node computes its weighted sum, a nonlinear function reshapes the output before it is passed forward. For hidden layers, the workhorse is the rectified linear unit, ReLU. ReLU has a beautifully simple rule. If the input is negative, output 0. If it is positive, leave it untouched. A bent line with the bend at the origin. That single bend is enough to break the linearity. And once linearity is broken, the network can describe curves, kinks, and regions where the answer flips. At the output node, a different function takes over. The sigmoid, or logistic, function squashes any real number into the range 0 to 1 with an S-shaped curve. Very negative inputs map close to 0. Very positive inputs map close to 1. That is what turns a raw weighted sum into something we can read as a probability. So pink goes in, numbers get multiplied, added, bent by ReLU, multiplied and added again, then squashed by sigmoid. This is forward propagation. 3 integers enter at the input layer, ripple through the hidden layer, and arrive at the output. Out the other end, 0.89. This is the first reveal. The mystery math is 2 operations, repeated. Weighted sum, then nonlinear bend. Weighted sum, then squash. Anyone who has ever fitted a line through a scatter of points has done the same kind of arithmetic. The only difference is depth. The only new ingredient is the bend in between. But that raises a sharper question. Who chose the 19 numbers? The weights and the biases? Not the engineer. The engineer chose how many layers there are and how many nodes go in each layer. That part is architecture. The numbers themselves, the actual values of W1 through W9, and the 4 biases were learned from data. Here's the second reveal. Learning in a neural network is a procedure for adjusting those 19 numbers so that the output of the network gets steadily closer to the truth, one small step at a time. The truth comes from labeled examples. For thousands of colors, a human has decided, this one looks better with light text. This one looks better with dark text. The labels are the answer key. For each example, the network is run forward with whatever weights it happens to have at the moment. It produces a prediction. Say 0.62 when the correct answer is 1. The gap between 0.62 and 1 is the error on that single example. Cost is how we measure that gap. The cost for a single example is the squared difference between the predicted probability and the actual label. Squared because we want errors in both directions to count equally, and because we want big errors to dominate small ones in the average. To reduce cost across the whole data set, we need to know exactly how much the cost would change if we nudged a particular weight up by a little. That sensitivity is a partial derivative. And there is one such derivative for every weight and every bias in the network, 19 of them in our case. The technique that calculates those partial derivatives for every parameter in the network all at once is called backpropagation. It runs the network in reverse. The error at the output is decomposed layer by layer into the contribution made by each weight and each bias upstream. The mathematical engine that allows this decomposition is the chain rule from calculus. The chain rule lets us untangle a deeply nested function, sigmoid of a linear combination of ReLU outputs, of linear combinations of inputs, into a clean product of simpler derivatives. For the weight feeding into the output node, for example, the chain rule gives a tidy 3-factor product. The activated hidden output times the derivative of the sigmoid evaluated at the output node times twice the prediction minus the truth. Every other weight in the network has its own 3 or 4 factor product of the same flavor. Backpropagation simply walks the network graph backward and gathers all of them in a single pass. Once we have a derivative for every parameter, we have a direction. To reduce cost, nudge each parameter slightly against its derivative. The size of the nudge is the learning rate, usually a small number like 0.01. Take one small step. Run the network forward on the next example. Compute the new cost. Take another small step. Repeat thousands of times across thousands of examples. That is stochastic gradient descent, the engine that does the actual learning. And one thing can sabotage the whole process. If the derivative at some layer is very close to 0, the parameter receives essentially no nudge. No nudge means no learning. Stacked deep layers compound this. Derivatives shrink layer by layer until the earliest weights barely move at all. That is the vanishing gradient problem, and it is the reason ReLU replaced older activation functions like sigmoid inside the hidden layers. ReLU has a derivative of 1 for any positive input, instead of a vanishingly small fraction. Input scale matters too. Feeding raw RGB values of 0 to 255 makes the weights compete against very large numbers. Dividing every input by 255 compresses everything into the cleaner range of 0 to 1, and training becomes noticeably more stable. And raw accuracy alone can lie. If 99% of the training colors take light text, a network can score 99% accuracy by always predicting light, without ever learning a single real pattern about color. The metric looks brilliant. The model has learned nothing. Imbalanced data demands smarter scoring, so the mystery math is no longer a mystery. It is multiplication, addition, a bent line, and a squash performed in sequence. The 19 numbers inside were tuned by reading the gradient of the error and stepping downhill, over and over. The structure is recognizable enough that the first version of these nets was sketched in the 1950s, then sat largely unused for decades. Two things changed after 2010. Data became abundant. Compute became cheap. The math itself had simply been waiting for both. Once they arrived, the same multi-layered regression started winning at problems people had quietly assumed required intuition. One caveat is worth holding. A network that learned to read X-rays at one hospital can fail at the hospital next door because the new machines produce subtly different images. A radiologist walks across the street and adapts in minutes, drawing on a lifetime of context that has nothing to do with X-rays. The network does not. The arithmetic does exactly what it was shown during training. No more and no less. Generalization, when the world shifts, remains the open problem.